Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Before we start today's video, I'd like to give a special shout out and huge thanks to our new respectable tribal elder, Omar Rayyan. Thank you so much for supporting the Game Engine series at this level. I'd also like to thank all Patreon supporters of this channel, who make it possible for me to spend more and more of my time creating videos about game engine programming. Speaking of which, we are now able to send any geometry data that we want to the GPU, and if we have been doing it right, all we need to do is to tell the GPU how it should render the geometry. Of course, we could load some shaders and run them in order to render any object, but we also need something that we could use to look at the scene. Something like an eye or, oh I know, a camera. Let's add cameras to our game engine. Let me start by doing a couple of fixes. This is kind of becoming a ritual for nearly every video, which is fitting since we are primals and primals love their rituals. Anyhow, here we need to use the array of GPU IDs and the offsets in order to return a pointer to the start of GPU IDs for any given LOD. And here we are asserting that the submesh index should be less than the maximum value that would fit in a 16-bit integer, which doesn't make sense because submesh index is already 16-bit and couldn't possibly hold a value that's larger. So let's make it 32-bit, although it's not recommended to have that many submeshes in a geometry asset. That's all for fixes. Let me close all files and add a new header file for the camera interface. The architecture that I'm going to use for lights and cameras is not set in stone and may be subject to changes in the future, as is the case for pretty much everything in the engine. But the idea is that cameras can be accessed in the game code, and therefore we need to put the interface in Engine API folder. Since this is a graphics item, we put it in graphics namespace. As we'll see later, a camera is associated with a game entity. As we move and rotate that entity, so does the camera. Similar to the entity class and the platform-independent surface class, it will have a dedicated ID type. The only member variable is a camera ID. Other data such as view and projection matrices and camera properties are exposed through a platform-independent interface as well. Before we continue, I'd like to explain a little bit about the camera types that I'm going to implement. In recent years, graphics rendering is becoming more and more based on physical properties of real-world objects. Obviously, that's where the term physically based rendering comes from. This approach is not limited to only the objects in a scene, but it can also be applied to lights and cameras. For example, we could model physical properties of a camera, such as the shutter speed, lens distortion, exposure time, and much more. Although this is an interesting topic to dive in, it's not really constructive to set up such a camera at this earliest stage of game engine development. Instead, we can take a more traditional approach of having a camera that gives us a projection matrix that depends on a small number of camera properties and the projection type. There are mainly two types of projection. The perspective projection resembles the way we see the world through our eyes, where objects look larger when they are nearby than when they are farther away. The second projection type is the orthographic projection, in which the size of objects doesn't depend on their proximity to the camera. You might think that this kind of projection is physically impossible. However, if the camera is really far away and zoomed in on a small part of the scene, the projection looks more and more orthographic. That's why this type of projection is used to render the scene from the viewpoint of the sun when rendering shadows that are caused by sunlight. Rendering shadows, however, is a topic for a later video. Let's examine the properties of each projection type. Starting with perspective projection, here we see the volume in which the scene objects are visible through the camera lens. When I move the camera around, the objects are viewed from different angles. As you can see, any object that's not within this volume, at least partially, is not visible on the screen. In particular, if an object is farther away from this plane or is closer than this plane, it will be clipped and not visible. These are called front and back planes, also known as the near and far planes. The ratio between the width and the height of the frustum is the aspect ratio of the camera, which is typically the same as the aspect ratio of the window to which we are rendering. The final property for perspective projection is the field of view of the camera. In most cases, it's expressed as the number of arc degrees in vertical direction. Both field of view and the aspect ratio can also be calculated from the view dimensions. For the orthographic projection, we need a rectangular volume where the front and back planes are the same size. In this case, we still need to know the camera range given by the near-Z and far-Z values. However, instead of aspect ratio and field of view, we need the view width and the view height of the camera in pixels. In the next video, we are going to look at how these projections can be expressed in mathematical terms, which can be implemented in code. We are going to have one camera class that can be created as a perspective camera or an orthographic camera. Therefore, we'll have some properties that only apply when the camera is of a certain type. For example, field of view and aspect ratio only apply to perspective cameras, whereas view width and view height are used for orthographic cameras. We can set some of the properties like the up vector, camera's field of view, the aspect ratio, view width and height, as well as the range in depth where objects will be visible. Depending on these properties and the projection type of the camera, the view and projection matrices are calculated. For convenience, we also calculate the inverse of projection, view projection, and inverse of view projection matrices. I'll explain how these matrices are calculated in the next video. We can also access other properties of the camera, along with camera type and the entity which this camera is associated with. I'll define an enumeration for the camera type as well. Next, we need to be able to create such a camera in the same way we create a surface, for example. I'll include the camera header here, but before we go any further, I'm going to tidy up the include directives in the engine. As you can see, we are using relative paths using .. for some of them and without .. for the others. And I would like to get rid of all .. So if you bear with me for a minute, I'm going to fix that. I'm also going to use forward slashes. I see I made a typo here. This should be perspective, which is a type of projection. Some of the header files can't be found this way. We can solve that problem by adding the engine path as one of the additional include directories in project properties. So basically select all projects that use headers from the engine and add solution dir engine to the additional include directories. There are still some ... slashes left, but those are all in engine test project, which is okay to be a bit messy. Okay, the engine builds and runs, and we can continue. So in the renderer.h, we need a function that creates a camera and another function that removes a camera. We need to tell this function what kind of camera it should create by providing it with a camera init info. This structure contains the ID of the associated entity, camera type, and the up vector. To save space, I'm going to use a union for field of view and view width, and a union for aspect ratio and view height. This is because field of view and aspect ratio are only used with perspective cameras, whereas view width and view height are only used with orthographic cameras. So basically we use two different names to refer to the same floating point value in each union. Although we could create a perspective camera using the view width and height, it's more intuitive to use field of view and aspect ratio. Finally, we have the near-z and far-z values for depth range. I'll also create helper structures with default values for each type of projection to make it easier for us to create cameras. The constructor takes the entity ID and fills in the rest of data with default values. For the up vector, we use the positive y-axis. Field of view is in units of 180 degrees, so a value of 0.25 is a quarter of 180, which is 45 degrees. And remember that this is in vertical direction. For the aspect ratio, I use a typical HD value, but it will be updated when we resize any window. In Primal Engine, I choose one floating point unit to correspond to 1 meter in real world. So for the near Z, we take 1 millimeter and 10 kilometers for the far Z. Obviously, that can be fine-tuned for each scene to achieve maximum depth precision. We repeat this for the orthographic camera, except now we set view width and height instead. Now we are ready to write create camera and remove camera functions. There is actually not much to write, because like most functions here, it's just a call to the low-level renderer using our graphics interface. But of course we need to extend this interface with new functions for the camera. This is also rather simple. We just add function pointers with the same signature. Then we can call these functions in renderer.cpp. Obviously, we also need to write the low-level implementation for creating and removing cameras, but let's implement our camera class first. There are quite a few member functions, so I'll copy them over and format the code so that the functions are ready for implementation. For each function, we need to call their low-level implementation using the API. However, that would add a lot of function pointers to our graphics interface, which I think is a bit of overkill. Now, because this project is a learning opportunity for myself as well, I'd like to explore new ways of doing things every now and then. And if it turns out that I made a poor design, we can always go back and do it the way that we already know it works. So in this particular case, I went all the way back to the 90s and looked at Win32 API, where there are functions that can be called to set and get different types of data, depending on some type of enumeration. For example, here we call setWindowLongPointer to set the user data as well as window style. And we let the function know which is which by giving it a parameter type constant. Let's define the parameter type constants for our camera class. I'll use an enumeration for this. Here we define one item for each camera property that we can set or get. Now all we have to do is to define just two functions that will set or get camera data depending on which parameter we are trying to set or get. Starting with the up vector, we can call the set parameter, giving it the camera ID, parameter type, and the data. We also provide the size of the data for an extra check that we can do later to make sure that we are reading from or writing to a valid range of memory. Field of view and aspect ratio are written in the same way, except their data type is now a floating point value. And the same holds for view width and view height. For camera range, we need to call this function twice, once for setting near Z and once to set far Z. Arriving at the getters, we now need to make room for the data that's returned, and calling getParameter function will write to that location. In case of view matrix, we need to make room to hold a matrix to which our getParameter function will be writing. Then we need to return this matrix. We do the exact same thing for other matrices, choosing the right type of parameter for each matrix. For getting camera's up vector and other properties, we need to use the appropriate return type. Not really exciting code, but it needs to be done. Now let's add the platform-specific camera class. It's very much the same as the platform-independent camera interface, but it holds all member data and it also gives the low-level implementation the freedom to include anything that's specific to the API. We have an update function that recalculates the matrices, and the rest is rather straightforward. One thing that's different here is that we use SIMD registers. Because we are going to access this data every frame, it's probably faster not to bother loading and storing data from memory. Here we still have one class for all camera types, and as we did for camera init info, we can use unions to give the same member variable two different names. It's not strictly necessary since it's private data and the difference could be handled by the accessor functions. However, this makes it more explicit and easier to follow in the actual code. When we call the update function, the projection matrix will be recalculated if any of these camera properties was changed. So we need a Boolean variable that we can set to indicate that something changed. Next, we'll add a CPP file for the implementation. Starting with the constructor, we use camera init info to fill in camera properties. Note that we don't have to set the view width and height variables, because they are aliases for field of view and aspect ratio. Then we call the update function that will calculate all matrices. I'll skip the update function for now, because I'm going to first explain what all these matrices are and how they are calculated, which is one of the topics of the next video. So click subscribe and hit the bell button if you'd like to get notified when that video is out. For the accessor functions, we can easily implement the getters by returning the right member variable. We could also implement the setters in the header file, but most of them are multi-line functions, and to keep things clean in the headers, I'm going to write them in the CPP file instead. these functions can't be constant anymore, because here we are modifying the member data. Now every time we change any of these camera properties, we need to set isDirty to true, so that the update function can pick up the change and recalculate the matrices. The update function is called once every frame, and we would like to minimize the number of calculations. Okay, we have written all member functions except one, which is the update function. As I mentioned, I'd like to write that code in the next video, because it involves quite a bit of math that I feel I need to explain, at least at a superficial level, to give an idea of how it works and maybe give you some pointers to start looking for a deeper understanding of the theory. With that in mind, I'm going to stop here for now, so thank you so much for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!